Okay, well we saw a very nice example of a group which was the strictly positive reals under regular multiplication. I'm going to give another example of a group which is going to consist of just a set of 0, 1 and 2 under addition modulo 3. So it's like clock arithmetic, but I'm going to consider addition modulo 3. And because I've only got a finite number of symbols here, I've only got so many different ways of combining them. Actually, for combining them, I'm not going to write that because it'll drive me nuts. What I'm going to do to combine them, I'm just going to write a dot. So we've got 0.0, 0.1, 0.2, 1.0, 1.1, 1.2, and then 2.0, 2.1 and 2.2. See how when I've written out all the possible combinations, I've structured it in such a way that makes it obvious that this list here is every possible symbol because I've combined every symbol with every other symbol. When you write out, when you're thinking about finite sets, it's always a good idea to try and put it in this thing here called a Cayley table. Okay, a Cayley table, and you normally put the group operation there, which is, I guess, addition modulo 3, but it's a bit of a fag to write it out over and over again. Okay, so addition modulo 3. 0 plus anything is the same thing. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2. 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 0. Because 3 is equal to 0, we're considering everything modulo 3. So the way I think about it is I'm sharing sweets out between 3 children, and then modulo 3 is how many sweets left over, and that's how many I get. So if there's 3 sweets in the packet, I give 1 to each child, and I don't get any. If there's 4 sweets altogether, then I get 1, because each child gets 1, and if there's, let's say, 10, then each child gets 3, and there's 1 left over for me. If there's 11, then that's equal to 2, because there's an extra 1. 12, I don't get any, because the kids get 4, and so forth. 2 plus 0 is 2. 2 plus 1 is 0, of course. 2 plus 2 is 4, which goes back to 1. So we can see that I'm combining each possible symbol with each other symbol in this Cayley table. You conventionally write the first one as a column and the second one as the row. So there it is. Now then, I assert that this is a group. Okay, so the 4 axioms are closure, neutral element or identity, neutral or identity, identity. I'm not quite sure why some people say neutral and some people say identity. Yeah, well anyway. Inverse, element, and my favourite, associativity. These are boring. Associativity is the interesting one. Okay, closure. Let's have a look at that. So I've got my set of 0, 1, 2. And closure basically says that we're mapping the Cartesian product of 0, 1, 2 cross 0, 1, 2, that's all ordered pairs, to the same set, 0, 1, 2. And so basically what that means is that there's no entry in this table here that's not present in the rows and the columns. So that's closed because that's satisfied because there's only 0s and 1s and 2s in the table itself. There's no extra symbol. Like, for example, here, when I said 2 plus 2, if I'd have written 4 there, if I'd have written 4, then it wouldn't be a closed operation because 4 doesn't appear in my set. I'm going to get rid of that 4 because it's annoying me. Where's my eraser? There it is. Get rid of that. Just a minute. It's better. Put that back to a 1, so it's closed again. Closure, tick. Neutral element. Well, of course, 0 is the neutral element because x plus modulo 3, 0 equals x. And of course 0 plus modulo 3, x equals x as well. So 0 will count as a neutral element. Inverse is a bit trickier. What we say is that for all x in the ground set 0, 1, 2, there exists x dash such that x x dash equals x dash x equals 1. Now again, I'm playing fast and loose with my operation because my operation is addition modulo 3, and I've denoted that here just by writing x just next to x dash as if I'm multiplying them together, and I'm not. So this is a sloppy notation. What I really mean is x plus modulo 3x dash equals x dash plus modulo 3x equals, oh, and I put a 1 as well. I've written the identity element as if it's a multiplicative identity, because of course if you multiply by 1, that's a neutral element under multiplication. What I really mean to say is equal to the identity element, which is of course equal to 0. Well, it's not equal to 0, it's equal to the symbol that I've denoted. It's equal to the group element which I've denoted by this sort of circular squiggle on my page here. Let's go back here to the symbol. I'm going to write it out again. Observe that when I'm thinking about this, and I'm somewhat thinking on my feet, I don't have any hesitation in writing it out again and again and again and again. 0, 0, 1. Doesn't hurt to write it out, just write it out again. Okay, so we need to check that this is satisfied for all x. So x equals 0. Well, of course, 0 plus modulo 3, 0 equals 0. Check. There it is. So the inverse element of 0 is 0. Well, we knew that, because e equals e. X equals 1. We've got 1, 2 equals 0. 1 plus 2, 1 plus 2 equals 0. And I better check it's the other way around. Yeah, 2 plus 1, so it's this row here and that column there, equals 0. That's good. Well, that's it. Because I've covered 0, 1 and 2, so each element, that one and that one and that one, each of them has a unique inverse, such that x dash equals the identity. But using the notation of this particular group, where the group operation is a sort of crossy thing with a little squiggle underneath it like that, x dash equals, and then the identity I wrote as a sort of round egg type thing here, which you're free to call a 0 if you want. So each element has got an inverse. Associativity is somewhat harder. Let's dispense with this plus 3 business. I've got to show that ABC equals ABC. Well, there's two ways to do this. The first way is to go through every combination of A's and B's and C's. So of course I've got 3 combinations for that, times 3 combinations for that, times 3 combinations for that. Altogether we've got 27 combinations. We might be checking something like 0 plus modulo 3, 2 plus modulo 3, 1 equals 0 plus modulo 3, 2 plus modulo 3, 1. And we'd need to do 27 different combinations of these things here to check that. But I'm not going to bother, because I'm going to observe that regular addition, integer addition at least, is associative. And integer addition modulo 3 plus modulo 3 inherits associativity from regular, normal, ordinary addition. Believe me, it is very much more efficient in terms of your time to see if you can show associativity by reducing it to some other operation which you're more familiar with than it is to go through all the possible combinations. Establishing associativity is quite hard. Okay, so there's a nice little group, addition modulo 3. I'm going to write it out again because I enjoyed it so much. Plus 3, 0, 1, 2, 0, 1, 2, 0, 1, 2, 1, 2. I'm filling it in a slightly different order. I'm using the fact to fill in here that 0 is a left identity, and I'm filling in these guys here by using the fact that 0 is a right identity. that must be a 2, because 1 plus 1 equals 2. That must be 0, that must be a 0, and that must be a 1. Okay, I'm going to stop there.